is going to hear some background noise. There's nothing I can do about it. Hopefully that it is not so noisy, then you can hear my voice clearly. Okay, let me also remind you that your first assignment is due tomorrow. Submit your assignment on e-learning. So tomorrow is the due date for your first assignment. Okay, so let us continue. So yesterday we discussed about time response of a first order system. And today we are going to talk about the time response of a second order system. So second order system, if we have the highest power of S in the numerator is 2, then that is a second order system. In general, the simplest second order system can be written as given on your notes. Here, K, omega n, and zeta are just parameters. They are just constant. It is written that way so that we can discuss the response depending on these parameters. These parameters are actually the property of the system. Depending on whatever mathematical model that we have, this K, omega n, and zeta represent some physical quantities. So this is in general the second order system. The transfer function of second order system looks like. Okay, example of second order system is this. This is, for example, you want to move, you want to control the displacement of translational mechanical system. This is going to be a second order system because you have a mass there and there is a second derivative, and then of course it's going to make the system second order. Okay, let's go to my notes. Okay, so for example, when you want to turn some inertia, for example, when you want to turn a robotic arms using a torque, so there is going to be a second order as well because of the Newton's second law. But here, if you this is the second order relationship between torque and theta. But if you have another motor here, motor itself is, as we have learned yesterday, a DC motor on its own relate to electrical voltage is already first order. So you have first order for motor, second order for the inertia, then the whole things here become third order. But anyway, the relationship between torque and theta here is second order. And then today we are going to learn how can we solve this, how can we get the time response of a second order system. So in general, this is the transfer function of the second order system. K is known as the system gain, omega n is known as the natural frequency, and zeta is known as the damping ratio. It is written, you might want to ask, why do we take all the trouble writing the second order system this way? Why not just some A divided by some constant divided by AS squared plus BS plus C, something like that? Okay, you can do that as well. There's no problem by doing that. But in that case, then the coefficient A, B, C in the denominator doesn't have any physical meaning. Okay, so that is why second order system is formulated such that it contains the gain K, the natural frequency omega n, the damping ratio zeta. Okay, so this is the transfer function of a second order system. So when we want to get the time response, we need to know what the input is. So for simplicity, let us assume the input is just the step input, which is 1 over S. And then let us just assume the system gain K is just equal to 1. So this is just for simplicity. Of course, for different type of input and for a different value of K, you're going to get a different response. But for the constant gain K, it's not so much. If k is other than 1, all you have to do is multiply the solution by k. Okay, now we want to see if we want to solve the time response when the input is a unit step. A unit step input, when you take the Laplace transform of unit step input, is going to be 1 over s. And then the output in terms of Laplace domain is just so multiplied by 1 over s, and then you have omega n squared divided by s, and then you have this quadratic equation. So there are three cases that we are interested in here. So if zeta here, if the damping ratio is greater than 1, and then you can factor out this quadratic equation. When you can factor that out, you can easily decompose this fraction, this expression into partial fraction. See, when zeta is greater than 1, you're going to have the roots of this quadratic equation is going to be distinct and real. It's going to be a real root, not some complex root. If the roots are real, then you can factor it out, and then of course you can now again perform your partial fraction, and then you can now have your time response by taking the inverse Laplace of that. So alpha and beta here is just the root of the quadratic equation. You can compute the roots using say negative b plus and minus root of b squared minus 4ac divided by 2a, the formula of quadratic equation. Again, this is the roots of the quadratic equation. If they are real and distinct, and of course you can factor it out, and then the time response of a second order system looks like just the first order system. So this is called the overdamped case. So when zeta is greater than 1, this is called the overdamped case. There are two cases. Another two cases is when zeta is less than 1. When zeta is less than 1, then the roots here is now become a complex root. You can no longer do this simple partial fraction. But we have talked about that. The solution is given in our previous class. So now we are going to look at if zeta is less than 1. So when zeta is less than 1, we have talked about this. You need to go back to our notes. This is just an exponential function multiplied by some sine function, where everything is defined here. Phi here is called the phase shift, and you can compute by arc cosine of zeta or arctangent of this expression. It's going to give you the same thing. And the frequency of oscillation now, instead of just omega n, you're going to have this omega d. Omega d is the actual frequency of oscillation. Omega n is known as the undamped natural frequency, or just the natural frequency. So this is a solution when zeta is less than 0. So to visualize this, you can now draw the response of second order system. It's going to be somewhat like this. So it's going, instead of just exponential increase, it is going to have some oscillation, and it's going to die out. So this is a typical response of second order system for underdamped case. So you can imagine. Let's go back to the example here. Okay, let's go here. So sometimes you're going to have oscillation. Sometimes, depending on the ratio of K, C, and M, sometimes you don't have oscillation. For example, the damping is large. So when the damping is large, there is no oscillation. The mass is just going to stop. But if the damping is so small, and of course when you apply a force here, sometimes a step force or whatever, sometimes it's going to oscillate, and then it's going to stop at its final value. So in general, when zeta is less than 1, then you're going to have some form of oscillation, and then the whole thing here is multiplied by some exponential function. So the detail of the response, so you can compute what is the rise time. So T out here is called the rise time. So the first time it hit the final value. T1 here is known as the first peak time. T2 is the second peak time, and TS is known as the settling time. When the response is already between 2% of the final value, we say that the system is already settled. So these are the values that we are interested in. And MP is how much the system overshoot from its final value. So all these parameters, all these quantities, the rise time, the peak time, the settling time, the overshoot will tell us the characteristic of a control system. So most of the time we don't want a very large overshoot. We don't like overshoot, and then we want the system to be settled as fast as possible. But most of the time you cannot fulfill those criteria at the same time. Sometimes you have to compromise. See, a large overshoot will give you a faster settling time, but sometimes a large overshoot is not desirable. Sometimes the system is slow reaching to the settling time, but there's no overshoot. There's always must be a compromise. So from this equation, okay, from this equation y of t, you can compute every single quantities that I have discussed there. So okay, so this is a peak time. The first peak time is given by pi divided by omega d. Omega d is just omega n multiplied by square root of 1 minus zeta square. This is second peak time. The rise time, this is the rise time. If you want to compute the rise time, this is a settling time, 4 divided by zeta omega n. If this is giving you overshoot, this is percent overshoot. Again, all this quantity will characterize the response of a second order system, depending on what you want to accomplish. Sometimes you want a settling time to be very small. Sometimes you don't want any overshoot. Sometimes you can compromise with overshoot as long as the settling time is very fast. But most of the time, you cannot fulfill the criteria at the same time. Most of the time, you are going to make a compromise. Okay, so these are the quantities that you can compute from the second order system, which in turns that you will know how the system behave, and then you can quantify whether it is satisfactory or not, depending on a specific application of your system. Okay, so now let's take a look at some of the example. Oh, okay. There is one more case. Okay, but here there is another case. See, when zeta is exactly equal to 0. So when zeta is equal to 0, everything will reduce just 1 minus sine omega n plus phi. See, if you substitute zeta is equal to 0, everything is going to be simplified. Okay, when zeta is equal to 0, which is called the undamped case. So when you substitute zeta equals 0 into that long equation, it's just going to reduce to this simple trigonometric sine wave. So your response is going to be oscillatory. Imagine if you have 0 damping, if you hang a mass to a spring, it's going to keep on oscillating. It's not going to stop because the energy is not going to dissipate. So for the undamped case, where zeta is equal to 0, then the response is just going to be oscillatory. So you have 3 cases of time response of a second order system. the idea is once you know the gain k, once you know the gain k, the omega n, and the damping ratio, you already know how the system responds. See, all you need to know is the gain k. If you know the gain k, and if you know the damping ratio zeta, and the natural frequency omega n, you already got the solution, because the solution just depends on these three quantities. That is why we categorize the control system according to order, regardless whether it is a translational system, rotational system, or whatever system. As long as you obtain the gain k, zeta, and omega n, you can now you already have the system response. All right, so let us take a look at some example. Okay, example 3. No, example 1. All right, so you're given this transfer function. So the transfer function of a second order system is given as 18 divided by s squared plus 3s plus 9. If you try to find the roots of this quadratic equation, it's going to be, I guess here is going to be a complex root. Okay, so here the question wants us to determine the gain, the undamped natural frequency, which is omega n, and the damping ratio. Once you have these three quantities, the gain, the undamped natural frequency, and then the damping ratio, you basically have the solution already. All right, so now let's take a look at the solution. All right, so this is the original transfer function, and then you can write this simply in this format. So you can now see that 9 is 3 square, 18 is 2 multiplied by 3 square, 3 is 2 1/2, 3. So this is in the format of k omega n square divided by s square plus 2 zeta omega n s plus omega n square. See, you just compare with the standard format. In fact, so now here you can see that k is equal to 2, there's a gain, omega n is equal to 3, and the damping ratio is equal to 1/2. In fact, you can solve this equation. You say omega n square is equal to 9, k omega n square is 18, 2 zeta omega n is 3. You can solve those three simultaneous equations and obtain this: k is equal to 2, omega n is equal to 3, zeta is equal to 1/2. Okay, so that this is the gain k, the natural frequency, and this is the damping ratio. Once you get these three quantities, of course, now you can draw your time response of a second order system. There's another quantities that you might be interested in is omega d. Omega d is the actual frequency of oscillation, which is just omega n multiplied by square root of minus zeta squared. So this omega d, it is slightly different from omega n. See, omega n here is 3. The actual frequency of oscillation is 2.59 radian per second. Why is that? Because we have a damping ratio here. We have a damper here, and then it's going to modify slightly the natural frequency. The natural frequency is when the damping ratio is 0. But with the presence of damping ratio here, the actual frequency of oscillation is going to vary slightly. So the computation of the actual frequency, which is omega d, is just omega n multiplied by square root of 1 minus zeta squared. So that is of your three parameters. Okay, so the next question, next example, example 2. See, it is given that a second order has undamped natural frequency, 12 radian per second, a damping ratio of 0.2. So find the damped natural frequency, the first and second peak, and percentage overshoot. So with this, when you want to quantify the behavior of control system, all you need is this: natural frequency and damping ratio. So you will know how much overshoot there is going to be, how fast the system response is going to be. So we can now compute all these quantities that is specified here. Okay. So we have natural frequency is 12 and the damping ratio is 0.2. Now you can compute the damped natural frequency, which is the actual natural frequency, omega n multiplied by square root of 1 minus zeta squared. So that's, you have 11.76. So this is the actual frequency of oscillation, slightly different from natural frequency. Natural frequency is 12, but the actual frequency now is going to be 11.76. The peak time is the first peak time, pi divided by omega d. The second peak time, 3 pi divided by omega d. So that's the value of first peak and second peak. Settling time is going to settle after 1.667 seconds. The overshoot here is 0.527, and the percent overshoot is 52.7%. So this is a very large overshoot, over 50%. So you can see whether this is satisfactory or not, depending on specific control system. But in this case, it looks like the percent overshoot is too large. So when you design the control system, you want the damping ratio to be a little bit higher than 0.2. Probably 0.5, 0.6, or 0.7. That will give you a smaller percent overshoot. But it's going to slow down the system response depending on the compromise that you can take. All right, so do you have any questions so far? Okay. What else do we have? Example 3. Okay. Before I go to example 3, do you have any question? All right, so let's take a look at example 3. Okay, so now this is a second order system. The second order system is shown in the figure below. A proportional control value Kp is equal to 20 is used. So this is the proportional control constant Kp. This is a design parameter. You can choose any value you like. In this case, it has been chosen for us Kp is equal to 20. You can choose any value you like. This is the proportional controller gain. It has been chosen for us 20. So the question is, if you choose the proportional constant to be 20, so we want to know how the system is going to behave. So we want to know what is the natural frequency, what is the percent overshoot, what is the settling time, probably what is the damped natural frequency as well, if the input is a unit step. Okay, so this is what we call the analysis problem. Given a control system, we want to analyze how it's going to behave. So the first step for you is to get the overall transfer function that relates input to the output. So you have this forward path, and this is the feedback gain is 1/6. So you need to get the overall transfer function, which is use G divided by 1 plus GH. And then from there, determine the system gain, determine the determine the natural frequency and the damping ratio. So your first step is to obtain the overall transfer function that relates from the output to the input. All right. So Okay, there you go. So the overall transfer function is for a feedback for a closed loop system is G divided by 1 plus GH. So this is G is the forward path transfer function. The feedback loop is just 1 over 6. Where the hell is 1 over 6? Wait a minute. Wait a freaking minute. Okay, this is 1 over 6 here. So this is H. This is H. Something is not right. Something is not quite right. Okay, this is G. Where is H? So it should be let me check my notes. Okay, make sure that this sometimes something's not right there. So see, the numerator here must be multiplied. So this is just G. So this is just 1 plus G. You need to have 1 plus GH. You need to multiply by 1 over 6 here. Multiply by 1 over 6. See, this is H. H is equal to 1 over 6. Okay, there is a missing 1 over 6 here. But this is correct. Okay, this is correct. See, so I missed 1 over 6. See, I'm very sharp. See, I can identify the error here. This is already correct. Once you simplify, this is already correct, and then now put in the standard format. Then you know that this is k is equal to 4.8, omega n is equal to 5, and zeta is equal to 0.6. Okay, make sure that you make correction to your notes, multiply that by 1 over 6. So you need GH there. Once you put in the standard format, then everything is now fall into place. So this is your gain, that is your natural frequency, that is your zeta, and then you can now compute all the various quantities. So omega d is the actual frequency of oscillation. You're going to get 4 radian per second. The settling time 1.3 second, and percent overshoot. See, percent overshoot here, if you notice here, percent overshoot is just a function of zeta. So when zeta is 0.6, so you have less than 10% of overshoot. If you want lesser than that, when you design a control system, you need to increase this damping ratio. So percent overshoot is just a function of damping ratio. When omega d and settling time is a function of both omega n and damping ratio. Okay. Do you have any question now? No. Okay. Yeah, moving along. I know some of you are sleeping. Is in the morning. Maybe there's a rain. It is raining at your place there. Probably you just cold and fall asleep. Which is I don't really care, right? Okay. Last example today. No, okay. All right, okay. I'm glad that you're still here. Okay, so example 3 is called the analysis part. Analysis type of question where the control system is given to you. All you need to do is analyze how the system behaves. So this example 4 here is a design question. So we have a unity feedback system is shown below. Determine the gain k. So k is the design parameter and appropriate value of p, so such that the following specification can be met. So you want the fastest response with less than 5% overshoot, and settling time is less than 4 seconds. So here you are given the specification. So you need to design meaning choose the value of K and choose the value of P such that the specification can be met. See? But here, for simplicity, let us just say we want overshoot to be equal to 5% instead of just less than, and settling time is equal to 4 seconds. Instead of less than, this is just for to simplify our discussion. Let's say we want to design the system such that the overshoot is 5%, and then the settling time is 4 seconds. K and P, we can design any value we like. It is just the property of the system. So what the value of K and P should you choose so that the settling time is 4 seconds and the overshoot is less than 5%. Again, we have discussed that the overshoot only depends on damping ratio. But your first task is to obtain the overall transfer function that relate between input and output. So the overall transfer function is G divided by 1 plus GH, not just K divided by S multiplied by S plus P. No, this is just the forward path transfer function. You need to obtain the overall transfer function. All right. Okay, so this is the overall transfer function. G divided by 1 plus GH. In this case, H is just equal to 1. So there's nothing missing here. Previously, we have missing 1 over 6. But here, the feedback path is just a unity feedback. H is equal to 1. So now this is your overall transfer function. And then simplify that. So now you have this second order transfer function for the system. K divided by S squared plus PS plus K. And then here we know that K is omega n squared, 2 zeta omega n is equal to P. But let us go back to specification. So we want the settling time to be equal to 4, and we want the overshoot equal to 5. Overshoot is just a function of damping ratio. So we can quickly solve for damping ratio from the overshoot. Percent overshoot is just a function of damping ratio. So now, if you want the overshoot to be 5%, it looks like the damping ratio must be 0.69. If you want the settling time to be 4 seconds, so settling time is 4 divided by zeta omega n, and then you get omega n is equal to 1.44 seconds. So now you have omega n and damping ratio. You can now solve for K and P. So K is equal to omega n squared from the from here you know that K is equal to omega n squared, 2 zeta omega n is equal to P. Okay, so K is equal to omega n squared, P is equal to zeta omega n, and then you get the value of K and the value of P. Incidentally, zeta omega n is equal to 1. Zeta omega n here is equal to 1. 1 multiplied by 2 is equal to 2. From that equation, you can see that for settling time is equal to 4 seconds, zeta omega n is equal to 1. And then you can quickly solve for K and P. So when K is equal to 0.1 and P is equal to 2, and then you can now fulfill the requirement of settling time is equal to 4 seconds and percent overshoot is equal to 5. So now we have seen two types of control system. One is the analysis. This is the analysis type of question. given a control system, you tell me how the system is going to behave. So there's analysis. And the second example here is a design type of example. I specify the specification, what the system should behave, and you tell me what you are supposed, how you are supposed to design the system. All right, so that's the end of today. We are done. I think that's the end of my notes today. That's the end. Okay, let me remind you again that your assignment is due tomorrow at 11:59 p.m. You can submit, the latest that you can submit your assignment is tomorrow, 11:59 p.m. E-learning says 2 days left. Yeah, it is approximately 2 days. Yeah, I know that. 1 day today and 1 day tomorrow. That's 2 days left, right? You have 1 day today. It's due on Thursday. Yeah. It due on Thursday. You have full day Thursday, and then you have full day today. There's 2 days left. Whatever it is, you need to follow. Today is Tuesday. Oh, okay. Sorry. Okay. Yes. Follow. I forgot. I thought today is Wednesday. Okay. No. Okay, sorry. Your assignment is due Thursday. Your assignment is due Thursday, 11:59 p.m. Sorry about that. I messed up. My mind is somewhere else. Okay, so that's it for today. I'll see you again next week. Keep working on your assignment. If you have any question, then you can ask all questions in our group chat. I'll see you next week.